So here we are in Objective 2 from Section 6.1. And remember, you need to fill in these definitions, and we'll start with our first guided practice activity. I'm going to leave it to you to do numbers 1 and 2. You're going to want to review your Chapter 4 notes. That's where we learned about rates and factors and the formula that gives you rates and factors. I am going to do this one for you because I'm going to do part of the next part for you. Now remember, the reason why that's 0.94 is because the factor is 1 minus, in this case, 0.06, because the rate is negative, and that's how I get 0.94. And I need that because I'm going to help you with this column, and I'm going to leave the others for you to practice. So in order to complete this table, from each row, I should say, to the next row, you have to multiply by the factor, which is why we needed to get the factors up here in part 1. That's why you need those factors. And that's how you're just going to get every number in each row. Multiply the previous numbers from the previous row by the factor each time. So for me, that means I have to take this 1,000 and multiply by 0.94. So if I multiply 1,000 by 0.94, I get $940. If I do it again, if I multiply that number by 0.94, I get $883.6. If I do it again, I get $830.58, and so on and so forth. So you can fill in most of this. Just keep going. I'm going to fill in the last one just so that you have a landmark and you know if you filled in the previous numbers correctly. Because if you get down here to number 10 and you get this number, that would only happen if you got all the previous numbers correct. So notice that each time we multiply by the factor, that's what makes this is what makes exponential growth. This is called exponential growth. When you're multiplying by some number each time, versus linear growth that we learned about in Chapter 5. In linear growth in Chapter 5, that was when you added or subtracted a number each time. This is different. We are multiplying by a factor each time. That's exponential growth. It's a big deal. It's the focus of Chapter 6. So if we go along here to number 4, write down a closed formula for each value in year 10. So you have to do that for each of these separately. You'll get a different formula for each. This relates to what we warmed up with at the end of the last objective. At the end of the last objective, we did that. Same thing here. Same thing. You start with your original amount, which for us was 1,000 across the board. So, oops, I went too far. So you start with 1,000 and you multiply by the factor, which in this case was 0.94, to the 10th power. That's what I would have for my rate of negative 6%. You need to do that again for the other rates. So this is only for the negative 6% rate. You need to try it for the other rates. And then if we move on here, we can move on to section 6.2. Now, some of 6.2 we're going to skip over, but some of it I want to be very clear on so that you know what we're skipping and what we're not. In section 6.2, we are going to focus on exponential equations of the form a times b to the x. These are the kinds that we're going to use. A is called the initial value, and b is called the growth or decay factor. So it would be growth if the rate was positive. It would be decay if the rate was negative. And this is a factor. Keyword factor. This factor word is the same word that you've learned already. So I'll show you how we construct those. We've already been doing it. We've been doing things like this. We just didn't use these letters before. So we like to compute exponential growth over time, because we are usually looking at things growing or decaying over time. You already know that this is how you compute a factor. And we're now introducing some new variables. Sometimes we use the letter P or Q. It doesn't actually matter what letter you're using here. What I want to point out to you is that little teeny tiny subscript O. That's not multiplication by O, that's a subscript O. That stands for the original amount of whatever it is that is growing or decaying exponentially. Versus P would be the amount you have after T amount of time. So I need to make sure that you can tell that this T is this one. So that's what these new variables are. So these are the kinds of things that we're going to do in 6.2. So here's an example, but you can ignore any reference to E, which is why we're ignoring the continuous growth decay rate. You can ignore any reference to E. This is another reference to E. We're going to skip that. And here we get back into equations of this form. So this is the format that we're going to use most often. And in your guided practice activity for 6.2, we're not going to use these graphs because see, all these graphs have E's in them. And we're skipping the use of E. So let me give you a different example to go with this part of 6.2. So I suggest you fill this in notebook paper. I'm going to do it off to the side here. And I'll give you an example instead of those graphs. So let's say we have a population of 5 million is decreasing at a rate of 4% per year. In part A, there'll be 3 parts to this problem. Let's create an exponential function of the form, well, the one I was just telling you, the one we're going to use the most, of the form P equals P subscript O 1 plus R to the T. So we need to create an equation like this. Well, remember back here, and pause this if I ever go too fast, okay? That's the beauty of a video. You can pause, fast forward, rewind. You can go as fast or as slow as you want. I was telling you back here that this P stands for the amount after T time. P subscript O stands for the original amount. T stands for time, and R stands for rate, and 1 plus R is a factor. So if we take that information and apply it to this example that I'm giving you, we can piece this all together. This is our PO. Let me color code that for you. This is our P subscript O because it's our original population. Okay, so we'll put 5 million in that part of the equation. We know our rate is 4%. So that means we'll have 1 plus, well, is it an increasing rate or a decreasing rate? It's a decreasing rate. So actually it needs to be 1 minus 0.04. That's how you get the factor if your rate is decreasing. You have to subtract to the T. They didn't tell us a time. This is just a function of time, so leave T. Leave this in the function until they give you a time. And leave P in the function, because if we don't know what the T is, we don't know what the P is. It depends on the T. So this is it. This is a function in exponential form. Now we can use that function to fill in a table. Let's fill in the following table. We're going to start with years in our left column of the table. Year is T. That's our time. We'll start with 0, 1, 2, and then I'm not going to do the whole table in the interest of keeping this video short for you. I'm going to stop at 10. And then we'll have the population, whatever this population is. I don't know if it's people or animals or bacteria. I don't know. It doesn't matter. It's exponentially decaying. The population at year 0, well, that'll just be 5 million because we haven't done anything yet. That's your starting point. That's your original amount. After 1 year, that's where you plug in 1 for T. So now we have a T value. So if we do that, if you plug in T to that equation, and you can use a calculator for this, you should get 4,800,000. If you plug in 2 to our equation, oops, and I meant to write 4T. That was 1. Here we're going to plug in for T to be 2. If we do that, and again, you get to use a calculator, you should get 4,608,000. And you could just keep doing that. Plug in 3, plug in 4, plug in 5. Let's go down and plug in 10. If we plug in 10, we should get 3, 3, 2, 4, 1, 6, 3. So 3,324,163, and I had to round that number, and that's okay. So that's how you fill in a table like this. That's what this formula is useful for, this function is useful for. And if you wanted to graph that, I'll show you what that looks like. Well, we started with 5 million, right? And the numbers went down from there. So since your numbers are going down, since your population is decreasing from 5 million, 5 million is going to be the highest point on the graph because it's going down from there. And we went all the way out to 10 years. So let's go all the way out to 10 years. So notice that T is on your horizontal axis. That should say years. And population is on your vertical axis, which is P. We always lay it out like that. Time always goes on the horizontal axis. P always goes on the vertical axis. And we got as low as about 3 million. So let's see. If this is where 5 million is, if I try to break this up somewhat evenly, that's close. It's not perfect. That's okay. 3,324,000 would be right around here-ish. Because right below that, that black tick mark would be 3 million. So that means way over here, when time is 10, we'll have a point. We have a point. Now, unlike linear functions that you learned about in chapter 5, this is an exponential function. Exponential functions are not straight lines. Linear functions are. Exponential functions are curved. So this one curves down because it was exponential decay, because they said our population was decreasing. They said our population was decreasing, so the curve goes down. Now, if the population were increasing, an increasing quantity would look like this. Hypothetically, it would curve upwards. But that's not what's going on in our problem. This is what's happening in our problem. If it was increasing, I should say, so that you realize that this is not part of our problem. If your population was increasing, then your graph would curve upwards.